We don't use any pen and paper. All digital things.
Campus is really beautiful.
Innovation 5.2 lab. We are able to control these drones with hand gestures.
Have a lot of games to play.
Yeah, so we don't have that much restrictions here.
Imagine this. You are using the latest AI itinerary planner. It's fast, it's polished, it's kind of amazing. In seconds, it can build your perfect 7-day Japan trip. Hotels, bullet trains, sushi spots, cherry blossoms, everything is sorted. You think, wow, this just saved me hours. But then, one of the top rated sites on your itinerary, it doesn't exist. Not a hidden gem, not an obscure local spot, just made up confidently. And this isn't just a funny travel fail. It's a symptom of a much deeper issue. Large language models like GPT, Claude, or Llama are brilliant at sounding smart, but the more we rely on them for legal help, medical advice, and financial insights, the same question keeps coming up. Can we actually trust what they say? Hey everyone, I am Pavani, member of technical staff at Microsoft. Welcome to this NIAT Masterclass on LLM evaluation frameworks and benchmarks, measuring what matters. So, in this masterclass, we will tackle the real question. How do we measure what truly matters in modern LLMs? Not just grammar, but truthfulness, helpfulness, safety, and domain-specific accuracy. In this session, we will go beyond outdated metrics and dive into cutting-edge evaluation techniques. How to use one LLM to evaluate another using structured, scalable methods. How to create dynamic, synthetic benchmarks for any domain you care about. We will understand how real companies use tools like MT-Bench, AlpacaEval, HELM, LM-Eval harness. How to audit your own models and know when they are hallucinating or getting off track. By the end, you will have a framework to evaluate LLMs not just on how they sound, but on whether they're actually right. You will get the most from this session if you are comfortable with Python and APIs, familiar with LLMs even at a basic level, and curious about how to make these models safer, smarter, and more reliable in the real world. Whether you are building LLMs, deploying them, or just trying to understand them better, this session will give you the tools to evaluate them the right way. So, let's dive in and figure out how to measure what matters. So, you have trained your LLM, you have prompted it to summarize an article, or maybe translate a sentence into another language. Then, naturally, you want to check how well it did. So, you run the evaluation and get results like BLEU 0.91, ROUGE 0.83, and F1 score 0.78. Those numbers sound pretty solid, right? But then a user reads an output and says, wait, the answer is totally wrong. So now you're scratching your head thinking, hold on, how can the scores look great but the answer still be wrong? Well, to figure that out, we need to take a quick step back. Let's ask, what are these scores actually measuring? Let's start with BLEU. Now, BLEU stands for Bilingual Evaluation Understudy. It was created for mission translation, specifically to check how close a mission's translation is to a human reference. So how does BLEU work? Well, it takes your model's output and it compares that to one or more reference answers, typically written by humans. Then, it looks at n-gram overlap, which is just a fancy way of saying how many sequence of words match up. These can be single words, 2-word combos, 3-word chunks, and the more overlap, the higher your BLEU score. Let me give you a quick example. Let's say the reference sentence is, the cat is on the mat, and your model says, the cat is sitting on the mat. Now, BLEU will notice overlaps like the cat and on the mat. Even though the phrasing isn't identical, the word sequences align fairly well, so the model gets a decent score. Sounds fair so far, right? Now, let's talk about ROUGE. ROUGE, which stands for Recall Oriented Understudy for Gisting Evaluation, is kind of like BLEU's cousin, but it was designed more for summarization tasks. So instead of focusing purely on precision, ROUGE leans towards recall, meaning it checks how much of the important content from the reference was captured in the summary. It still looks at word overlaps and sequences, but with a different goal. Did the model include all the important stuff? It's like asking, okay, the model summarized the article, but did it remember the key points? So, BLEU is about how similar the words are, and ROUGE is about how much was remembered. And finally, there is F1. Now, you have probably seen this one before, especially in classification tasks. F1 combines precision and recall into a single number. Precision answers, out of all the things the model said, how many were correct? Recall asks, out of all the correct answers, how many did the model find? And F1 is the harmonic mean, so it balances both. It works great when your LLM is doing structured tasks like pick A, B or C or extract all the cities mentioned in this paragraph. So, now you have probably wondering, if these metrics are so well established, why aren't they enough for LLMs? Let's break that down. Let's go back to BLEU. It's only measuring word overlap, not meaning. Imagine you ask an LLM, translate how are you into French, and the model says comment ça va. That's a completely natural translation. But what if your reference answer was comment allez-vous, a more formal version? Now, BLEU sees two different phrases with low word overlap. So it gives a low score even though both translations are totally correct in real life. You see the issue? BLEU doesn't understand the meaning. It just sees word patterns. It's like grading two chefs based on how closely their dishes match a photo instead of, actually tasting the food. ROUGE isn't perfect either. ROUGE assumes there is one right summary when in fact there could be many. Take a news article. One summary might emphasize the timeline. Another might focus on the underlying causes. Both are valid. Both are helpful. But ROUGE only compares to one reference, so even a well-written answer might get penalized. And F1? It has limits too. F1 shines when the task has a clear answer like extract the list of countries mentioned. Great, you can check whether the model found them. But what if the prompt is more open-ended, like write a helpful reply to this customer email or suggest ways to improve this paragraph? There is no fixed set of correct tokens in these cases. So F1 doesn't really know what to do and the score becomes meaningless. Let's take a moment to summarize what we have just covered with a quick side-by-side breakdown. BLEU was built for translation tasks. Its strength lies in detecting n-gram overlap, those short word sequences. But it ignores things like meaning or tone, which we know matter a lot in real-world communication. ROUGE, on the other hand, was designed for summarization. It's great at checking recall, whether key points were captured, but it often penalizes valid alternate summaries, even if they are equally accurate or helpful. And F1 score, as we said, works really well for classification or named entity recognition, these binary yes or no tasks. But it breaks down when there is no single correct answer, which is exactly what makes LLMs powerful. Now, let's try to understand how these metrics are computed in a hands-on lab. In this lab, you will learn how to evaluate the outputs of large language models using classic NLP metrics BLEU, ROUGE, Meteor, BERT score, and F1. We will define example predictions and references, compute each metric step by step, visualize and compare metric scores, and discuss the strengths and limitations of each metric. By the end of this lab, you will understand how these metrics work, how to apply them to your own models, and why modern evaluation often requires more than just traditional scores. Okay, let's install the required packages. We need evaluate to evaluate BLEU and ROUGE scores, and NLTK for WordNet libraries. Let's import the relevant libraries. Here we have some example predictions and references. Let's take for example, our reference is capital of France is Paris and our prediction is also the capital of France is Paris. And let's take another reference. Boiling point of water is 100 degrees Celsius and our prediction is water boils at 100 degrees Celsius. And let's see what these traditional metrics will give. So here is BLEU. We already discussed what BLEU is. This is the mathematical representation of BLEU, where R is the reference length, C is candidate length, and Wn is weight for n-gram, and Pn is n-gram precision. Let's evaluate BLEU for our predictions and references. So we see here that BLEU score is 0.323. So even though our predictions and references are pretty similar, but we see here that BLEU score is pretty low. So let's see what ROUGE metrics gives us. So this is the mathematical representation of ROUGE. It's basically the longest common subsequence between your reference and prediction by the maximum length of reference and prediction. Let's install ROUGE score to compute the ROUGE metric. Let's evaluate ROUGE metric now. We see compared to BLEU, ROUGE has improved from 0.3 to 0.5, but still we see our predictions and references are pretty close, but still we see a lower score. Let's see other metrics. This is the F1 metric, which is basically precision into recall by precision plus recall. And let's see what is the score for F1 metric. So we see here that F1 score has improved compared to BLEU and ROUGE, but still this is not really high because our predictions and references are pretty close. We still are seeing a large gap in the scores. Let's go to Meteor. Meteor improves upon BLEU and ROUGE by considering synonyms, stemming and paraphrasing. So let's run Meteor and see what our score is. Meteor improved upon BLEU, ROUGE and F1, but still we see a large gap in the prediction scores compared to our references because predictions and references are pretty similar. Let's go to BERT score. BERT score leverages deep contextual embeddings from models like BERT to compare candidate and reference texts. Basically, it captures semantic similarity beyond surface word overlap. This is more suitable for modern NLP tasks. Let's install BERT score. Let's compute our BERT score now. We are downloading the BERT model now. It might take a little time. We got our BERT score. It's 0.937. This is really accurate compared to ROUGE, BLEU and F1 metric because BERT is based on semantic similarity instead of word overlap. Let's visualize our metric scores now. We can see that for the capital of France is Paris, even our reference is the same. That's why all of these metrics scored really high. But for something like water boils at 100 degrees Celsius, because our reference was boiling point of water is at 100 degrees Celsius, the word overlap between prediction and references is really low, and that's why traditional metrics like BLEU, ROUGE and F1 scored really low compared to BERT. This is similar with other predictions as well. The BERT really scores high compared to these traditional metrics because the BERT score is based on semantic similarity. So now, We understand what BLEU, ROUGE, and F1 actually do. We have seen how they measure surface similarity, n-gram matches, overlaps, binary correctness, but not the deeper stuff: factuality, instruction following, helpfulness, tone, or safety. And here's the real turning point. LLMs don't just generate answers, they generate open-ended, diverse, and often creative responses. Sometimes, multiple answers can be equally valid depending on the user, the context, and even the tone. So the question becomes, what do we actually want to measure? When we evaluate LLM performance, what we are really asking is, was it factually correct? Was it helpful to the user? Did it follow instructions accurately? Did it strike the right tone? Formal, casual, respectful? Did it behave safely and avoid bias or toxicity? And honestly, most of those are really hard to score with a simple number, especially when there is no ground truth or only subjective expectations. This is where things start to get interesting, because there is a new idea, a radical one, that's quickly gaining momentum in the AI community. What if we used LLMs to help evaluate other LLMs? Yes, really. Instead of relying solely on fixed metrics or human reviewers, we let large language models serve as judges, comparing responses, applying rubrics, and even writing feedback. That's what we will explore in the next chapter. It's called LLM as a judge, and it's quietly transforming how we measure model quality from pairwise ranking to rubric-based grading. Let's dive in. At its core, it's exactly what it sounds like. We take a powerful general purpose model like GPT-4 and we ask it to evaluate outputs from another model. But we don't just throw in the answers and hope for the best. We guide the evaluation with a clear scoring prompt, a well-defined rubric, and sometimes even ask for comparative judgments. There are two common patterns this takes, so let's walk through both. First, pairwise comparison. In this setup, we give the judge two different responses to the same prompt, and then we ask a simple question like which response is better or which is more accurate, more helpful, and more aligned with user's intent. The judge, the LLM, looks at both responses and casts its vote. That's it. It doesn't score each answer separately. It just picks the better one. This method is used in several popular tools: MT-Bench for multi-turn reasoning tasks, AlpacaEval to test fine-tuned models, and Chatbot Arena where two models compete head-to-head in a public leaderboard. We will take a closer look at these in just a moment. Now, let's discuss rubric-based evaluation. The second approach is a bit more detailed and much more customizable. Here, instead of asking which is better, we ask the LLM to assign scores across specific dimensions like factual accuracy, relevance to the prompt, clarity and tone, safety, or absence of bias. Each of these comes with a rubric, basically clear guidelines on what a 5 versus a 2 looks like. Here's an example prompt you might use. You are a helpful assistant evaluating student answers. Please assign a score from 1 to 5 on factual correctness, relevance to the question, and completeness. Justify each score in one sentence. This approach is super useful for complex domains like healthcare, education, legal analysis, and customer support, where a binary yes or no or winner or loser doesn't cut it. But wait, can we trust a model to judge another model? That's the million-dollar question. Let's talk about why this works and where it might break down. There are some serious advantages to using LLM as a judge. It's scalable. You can evaluate thousands of responses without needing a team of human annotators. It's fast and low cost. No hiring, no training, no QA overhead. It's flexible. Change your rubric in seconds to fit a new task or domain, and it's language agnostic. It works across languages, even for code. Pretty compelling, right? But like everything in AI, there are trade-offs. Let's be real. The method isn't perfect, and here's why. Number 1, evaluator bias. If your judge model has preferences like always favoring longer answers or liking certain styles, it can skew the results. It might reward style over substance. Number 2. Model collapse. If everyone uses the same LLM to both train and judge models, we risk ending up in a feedback loop where all models start sounding the same. Number 3. System gaming. Some clever models can be fine-tuned to trick a specific judge, gaming the system without actually improving quality. Finally, rubric drift. If your evaluation prompt is vague or it changes slightly over time, your score loses consistency, and that's dangerous when comparing models at scale. Let's look at a few real tools using LLM as a judge. First, MT-Bench. Focused on multi-turn dialogue, LLMs are asked step-by-step reasoning questions. GPT-4 ranks which answer is better, and it is used heavily for chatbot evaluations. Second, AlpacaEval. Built for evaluating fine-tuned LLMs, uses GPT-4 or Claude to vote between outputs. It's open source and works well with Hugging Face models. Third, Chatbot Arena is a crowdsourced leaderboard. Users vote on head-to-head model comparisons without knowing which model is which. Results are ranked using ELO rating like in chess. Fun fact, even the creators of GPT-4 track their model's performance here. So far, you have learned that LLM as a judge is a way to let one LLM evaluate another. There are two common methods: pairwise comparison, which is simple and fast, and rubric-based evaluation, which is flexible and nuanced. Tools like MT-Bench, AlpacaEval, and Chatbot Arena are already using this at a production scale. It's fast, it's cheap, it's surprisingly effective, but like all powerful tools, it needs careful design to avoid bias, collapse, and overfitting. In the next module, we are going hands-on. You will get to run your very first mini evaluation, where we will use GPT-4 to judge two model responses to a real prompt and pick the better one. It's time to judge the judges. Let's get to it. Alright, now that we understand the idea of LLM as a judge, it's time to see it in action. In this hands-on segment, we are going to simulate a real evaluation scenario. Here's the setup. We will take a sample prompt, something open-ended and subjective, like a summarization or reasoning task. Then we will show two model outputs, let's say from model A and model B, and we will ask GPT-4, our evaluator, to decide which output is better based on a clear predefined rubric. This is exactly how systems like AlpacaEval or MT-Bench work, just on a smaller scale. We will show you how to format the input properly, write the evaluation prompt, interpret the results, and avoid common pitfalls in judgment. Let's jump into the code and see how it works. Let's install and import required libraries here. Here we are reading the OpenAI secret key. Let's install few more libraries required like Evaluate, ROUGE, and Rich for printing. Here is our article. NASA's Perseverance rover successfully landed on Mars in February 2021. Its main mission is to search for signs of ancient microbial life and collect rock samples that might later be returned to Earth for study. Here is our reference summary. NASA's Perseverance rover landed on Mars to look for ancient life and gather rock samples. This is our GPT model summary. In 2021, NASA placed the Perseverance rover on Mars to explore the planet's past habitability and collect stones for future research. So if you look at the reference summary and GPT summary, this is very close to the article summary. Let's see what our ROUGE score is for this summary. Let's compute ROUGE score here. Here we see that our ROUGE score is pretty low, 0.36. Though our GPT model summary is very close to our reference summary semantically, but because we have less word overlap, our summaries, the ROUGE score is very less for these summary. Now let's use our LLM as judge and see what LLM as judge scores for this summary. Here is the prompt. You are an expert evaluator. Compare the model summary with the reference summary. Rate how well the model summary captures the meaning of the reference. Even if the wording is different, score 1 to 10, 10 for perfect meaning match. Respond in JSON with score and justification of why the score. And we'll pass in the article, reference summary, and the model summary. And here we are calling OpenAI Chat Completions API and pass the model. We are using GPT-4 as the model. And we use temperature 0 and max tokens 150. If we wish, we can change the temperature and max tokens accordingly. Let's see what LLM has judged scores. You see our LLM has judged score 9 by 10. And the justification is model summary accurately captures the main point of the reference summary. Even though we have pretty less word overlap between our reference summary and GPT summary, LLM as judged semantically captured the meaning and scored it pretty high, which ROUGE couldn't do. Let's compare the results. Our ROUGE score is 0.36 and LLM as judged score is 9. That's why we can trust LLM as judged because it semantically captures the meaning. Let's look at a different example. CNN Daily Mail dataset is a benchmark corpus for abstractive text summarization. Here we have article, which is the full news story text and highlights the human reference summary. We will compare ROUGE versus LLM as judged. Let's load the dataset here. Let's wait for the dataset to load completely. Here is some sample article from CNN dataset. So this is an article and reference summary. Here our reference summary is: Julie decided to give a kidney to a stranger. A new computer program helped her donation spurred transplants for 6 kidney patients. Let's see for this reference summary how our models predicts the summary and also how ROUGE and LLM as judged scores for this summary. So here we are comparing two different model pairs, GPT-3.5 Turbo versus GPT-4o Mini and GPT-3.5 Turbo versus GPT-4o, and see which model scores better. So here is the rough estimation of GPT-3 model parameters. GPT-3.5 Turbo has around 20 billion parameters, GPT-4o Mini has around 8 billion parameters, GPT-4o has roughly 200 billion parameters, and the latest model like GPT-4 has 1.8 trillion parameters. GPT-4 is the model which we are using as a judge to evaluate these models. And we will do ROUGE evaluation and also LLM as judge evaluation to compare these metrics. Let's import the required libraries. We'll import OpenAI for OpenAI Chat Completions API calling, and we'll import Evaluate, Matplotlib, NumPy for plotting and printing. Here we'll write our summarization function. The summarization basically takes the model name and article and asks LLM like OpenAI models to generate summary for that article. So here we use temperature and max tokens. Temperature basically controls the randomness or creativity of the output. If it's lower value, it's more focused, factual and deterministic results. If it has higher value, it creates more creative and varied summaries. If you want more creative outputs, we can increase the temperature accordingly. And we can increase max tokens if you want the summary to be more detailed. Let's compute the ROUGE score here. And now here we define LLM score judge. So this is the prompt for scoring LLMs. You are an expert summarization evaluator. You will rate 2 summaries of the same article on a scale of 0 to 10 based on these criteria: faithfulness, coverage, coherence, and clarity. Then choose which summary is overall better and explain briefly. We will pass in article, reference summary, summary of model A and summary of model B. And we will ask LLM as a judge to respond in this format, like where we will have score for the model A, score for the model B, which is better, whether model A scores better or model B, and also justification on why the model A or B scored better. And here we are calling OpenAI Chat Completions API to generate the response. In this code cell, we will compare models. We will have two models, model A and model B, and our judge. We will generate the summary and then compare the ROUGE metric for these two models. Here we will call LLM as a judge. LLM as a judge takes articles, references, summaries of model A, summaries of model B, and then it will call LLM score judge method internally, and it will create results for these model A's and model B. In this function, we are aggregating and displaying all the metrics. Let's call the compare models again to generate summaries and also print the summaries, ROUGE metrics, LLM as judge evaluations, and return all the results for model A, model B, and scores for model A and model B. Now, this is the code cell where we get results for all the cells. So we are comparing two models, GPT-3.5 Turbo and GPT-4o Mini, and we are using judge as GPT-4. And in this second comparison, we are comparing GPT-3.5 Turbo with GPT-4o, and then we are using GPT-4 as a judge. Let's run to compare. Let's wait till it generates summaries. Okay, now we generated summaries for GPT-3.5 Turbo and GPT-4o Mini. Now this is our summary, reference summary. Julie decided to give a kidney to a stranger. A new computer program helped her donations per transplants for 6 kidney patients. And if you see the GPT-3.5 Turbo summary and GPT-4o Mini summary, these summaries fully captured the reference summary, whatever is in the article. So it says, Julie Broussard, selfless kidney transplantation led to a chain of 6 transplants. Even with GPT-4o Mini, we see the similar summary response. But if you can see the ROUGE scores, the score is pretty low because ROUGE works with word overlap. But if you can see LLM as a judge score, we see the scores pretty high for both the models, GPT-3.5 Turbo and GPT-4o Mini. And the LLM even generates which is better. Because GPT-4o Mini scored higher, model B is better. And it also generates a justification why model B is better. This is again the model comparison for GPT-3.5 Turbo versus GPT-4. And even here we can see that GPT-4o summaries pretty well captures our reference summary, but the ROUGE score is pretty low for even this. But as LLM as judge, the score is pretty good. And we can even see which model is better with justification. And this is our overall model performance. And let's see some charts to visualize these results. Here you can see the GPT-3.5 Turbo, GPT-4o Mini, GPT-4o clearly captured the summary pretty accurately, but the ROUGE scored pretty low for these models, but LLM as judge did a pretty great job in scoring these models. And there you go. You have just built a mini LLM evaluation pipeline using GPT-4 as your judge. In a few lines of code, you have done what used to require hours of human annotation, and you have done it consistently, scalably, and transparently. This technique is quickly becoming a standard in both research and production. Whether you are comparing two fine-tuned models, evaluating outputs from prompt chains, or monitoring response quality, LLM as a judge gives you a powerful new lens. In the next module, we will scale things further. What if, instead of evaluating just 2 responses, you could generate entire synthetic benchmarks using LLMs? That's what we will explore next. LLM generated benchmarks. Why they matter, where they shine, and how you can build your own. Let's move on. Let's imagine this. You want to test how well your LLM handles finance-specific reasoning. Maybe you are building a virtual CFO, or testing a model for regulatory compliance. What's your first instinct? You sit down to manually write out 100 prompt response pairs. You carefully curate examples, label the expected outputs, and maybe even bring in domain experts to review everything. And it works. But let's be honest, that's a huge time sink. It takes days of effort, it's tedious, it's expensive, and it definitely doesn't scale. Here's the real question. Can we use LLMs not just to answer test questions, but to actually generate the benchmarks themselves? And the answer is yes. In fact, this idea is already reshaping how we evaluate modern language models. Let's pause here and define what we mean by a benchmark in the context of LLMs. A benchmark is simply a standardized test, a consistent way to measure how well a model performs on specific tasks. Traditionally, these benchmarks have been manually written, fixed in content, or often domain-specific, like law, biology, or programming, and updated very slowly. But LLMs evolve fast, which means static benchmarks age quickly and start to fall behind. That's where LLM-generated benchmarks come into picture. What are LLM-generated benchmarks? LLM-generated benchmarks are exactly what they sound like. Test datasets created by language models. Here's how it works. Instead of having humans write out every question and answer manually, we prompt a powerful LLM, something like GPT-4 or Claude, to do the heavy lifting, generate realistic, high-difficulty questions, produce multiple possible answers, good and bad, label the best answer, and explain the reasoning behind the label. Think of it like this. Instead of using the same workout routine for months, you have now got a smart fitness coach generating a new personalized workout every single day based on your progress, your goals, and even your energy level. That's what LLM-generated benchmarks bring to evaluation: freshness, adaptability, and precision targeting. There are 4 big reasons why this matters. First, freshness. As the world changes, new medical guidelines, financial regulations, or pop culture trends, your benchmarks can adapt in real time. Second, domain coverage. Want to test legal reasoning, aviation safety, high school physics? No problem. LLMs can generate domain-specific challenges instantly. Third, skill targeting. Need to evaluate analogy reasoning, chain of thought prompts, coding edge cases? Just change your generation prompt. And finally, scale. You can spin up thousands of test cases in just a few minutes across topics, difficulty levels, or languages. Here are few tools and research efforts already using this technique. Number 1, HELM by Stanford. HELM stands for Holistic Evaluation of Language Models. It combines manual and synthetic tasks to test models on multiple fronts: accuracy, bias, robustness, efficiency, and more. Number 2, GAIA, General AI Evaluation, was designed by a mix of academia and industry. It uses dynamic prompts to generate a wide range of tasks, especially focused on world knowledge and reasoning. And best of all, it's updated frequently so it stays current. ZBench. ZBench is all about hard reasoning problems. It uses LLMs to generate multi-step, logic-heavy, even intentionally tricky questions, especially in domains like math, programming, and symbolic reasoning. Now, this all sounds powerful, and it is, but there are still a few cautions to keep in mind. First, bias amplification. If your benchmark generating LLM has biases, it may create biased test sets, and those biases will get baked into your evaluation. Second, task leakage. If your model has seen similar tasks during training, it might recognize the benchmark and perform unusually well. This gives you a false sense of performance. Third, quality control. Even generated benchmarks need spot checks. You still want to validate your tasks, make sure they make sense, aren't misleading, and actually test what you care about. So far, here's what you have learned. LLMs can now generate their own test datasets, not just answers. This makes benchmarking faster, broader, and way more customizable. Tools like HELM, GAIA, and ZBench are already proving the value of this approach. But as always, quality, bias, and overfitting are still things to watch. Now, that we have talked about how to generate benchmarks, what about actually running these evaluations? In our next segment, we will roll up our sleeves and explore tools like LM Harness, APIs from providers like OpenAI, and custom rubric style prompt templates to score your models. From theory to pipelines, that's what's coming up next. Let's keep going. Alright, so we have seen just how far LLM evaluation has come. We started with rigid metrics like BLEU and ROUGE, then moved into dynamic LLM generated benchmarks, and even saw how one LLM can judge another. But now, let's get practical. What are the actual tools, the frameworks, and systems you can use to run these evaluations today? The good news, you don't need to reinvent the wheel. There's a powerful ecosystem of open source libraries, research-grade dashboards, and enterprise frameworks ready to plug into your workflow. Whether you're an ML researcher, a product engineer, or building in-house LLM apps, there is something here for you. Let's walk through the most important ones. First, LM Eval Harness. Think of this as your baseline testing rig. It's a command line tool that lets you run your LLM across standardized benchmarks like MMLU, HELM, ARC, Truthful QA, and more. In a way, it's like PyTest, but for language models. You plug in your model, whether that's OpenAI, Hugging Face, or a local one, and run consistent reproducible evaluations. It supports zero-shot and few-shot testing, YAML-based config, and custom prompt templates. It's especially great if you're benchmarking base models for comparing architectures side by side. Number 2, HELM by Stanford. The full name is Holistic Evaluation of Language Models, and the name says it all. HELM doesn't just check if your model is accurate, it also tracks bias, fairness, robustness, toxicity, and efficiency. So, instead of a single number, you get a multi-dimensional profile, super valuable if you're working in socially sensitive or high-stake domains. Third, Dynabench. Now this one's all about real-world stress testing. Dynabench uses a human-in-the-loop setup where actual users try to break your model with edge cases, tricky prompts, and adversarial inputs. It's like a bug bounty but for language models. The system collects hard examples, updates the benchmark dynamically, and helps you uncover weak spots you didn't even know existed. Use Dynabench when you want to test for robustness in the wild. Number 4, GAIA Leaderboard. GAIA stands for General AI Evaluation, and it's a community-led effort to benchmark LLMs using synthetic tasks, LLM as a judge scoring, crowd-based aggregation. Think of it as a real-time scoreboard for the LLM world, tracking how models stack up against each other over time. Whether your model is open source or private, GAIA gives you a sense of where you stand in the global landscape. Also, we have a few enterprise frameworks. First, OpenAI Eval's Toolkit. This is a Python-first framework for defining evaluation scenarios, automating test cases, running scoring logic on the backend, integrating directly with fine-tuning workflows. It's great if you're deploying LLMs in production and need repeatable internal testing. Second, Anthropic's Constitutional Evaluation. This one's fascinating. It uses a value-based rubric like honesty, helpfulness, and harmlessness, and gets the model to self-critic based on those values. Basically, the model grades its own behavior using predefined principles, very useful in safety-critical or alignment-sensitive applications. Apart from these, you can DIY with GPT-4 or Claude. And of course, if none of these frameworks fit your exact use case, you can always roll your own. Just use GPT-4 or Claude as a judge, structured rubric-style prompts, JSON-based scoring, and a bit of aggregation logic. This works incredibly well for small labs, custom domains, or when you are building something too new for public benchmarks. So here's how you can choose the right evaluation tool based on your goals. If you're doing academic style evaluations and want standardized metrics, go with LM Eval Harness. If you care about social and ethical diagnostics, HELM gives you that multi-dimensional lens. For real-world robustness, Dynabench helps you capture edge cases that traditional tests miss. Need to see how your model stacks up publicly? GAIA's leaderboards gives you the big picture. Building in the enterprise, tools from OpenAI and Anthropic are tailor-made for production. And for everything else, quick experiments, niche use cases, internal evals, just DIY it with GPT-4 or Claude. So far, you have seen the key tools in the modern LLM evaluation stack, how each one serves a different purpose: technical, ethical, domain-specific, or production scale, and how to mix and match them to fit to your use case and budget. Whether you're fine-tuning a chatbot or shipping a safety-critical app, there is a framework out there to support your evaluation journey. Alright, now that you have got the lay of the land, it's time to get hands-on again. In the next module, we'll walk through a live demo. You will learn how to use LM Eval Harness or spin up your own rubric-based evaluator using GPT-4 to compare multiple model outputs at scale. It's practical, it's flexible, and it's built for real-world production-ready use. Let's dive in. Now that you have seen the landscape of evaluation tools, let's get our hands dirty again, this time with a scalable evaluation workflow. In this mini lab, we will show you two paths using LM Eval Harness to run standard benchmarks like MMLU, BLEU, and GSM-8K on your own model. Use zero-shot and few-shot prompts along with other task-specific configurations to evaluate the same task from multiple perspectives for comparison and more flexibility. We will cover how to set up your model backend, configure the task and few-shot examples, run the evaluation and interpret the output, and adjust task-specific configurations for different scoring dimensions. These workflows are modular, meaning you can swap in different models, datasets, and criteria as needed. Let's jump into the code and walk through it together. So we are going to demonstrate LM Evaluation Harness. LM Evaluation Harness is an open source framework designed to evaluate large language models. Here are some of the key features: unified interface, extensive benchmark coverage, custom model integration, reproducibility, and extensible. Let's install required libraries here, which is LM Eval for LM Evaluation Harness and OpenAI for OpenAI Chat Completions API. Let's read our OpenAI API key here. Let's get into our first task, BLEU. BLEU is a natural language understanding benchmark introduced as part of SuperBLEU suite. It consists of yes or no questions paired with passages from Wikipedia. The task type is binary classification. And why is it challenging? Because it involves deep reading comprehension, common sense reasoning, ability to handle negation, implicit interface, and ambiguous phrasing. So here is one example from the dataset. Example passage: bananas are botanically classified as berries because they develop from a single ovary and contain seeds. Let's say our question is, are bananas considered berries? And our ground truth is yes, because our passage contains this statement. Let's get our hand dirty with calling OpenAI models with BLEU dataset. So here we are loading dataset, reading the passage, questions and reference answers, and we are sending the prompt, answer the question with only yes or no, and passing the passage, question, and asking LLM to answer. By the way, here we are not using LM Eval Harness framework, and if you see, if we don't use LM Eval Harness framework, we have to write a lot of lines by passing the prompt, by asking the model to respond, and also reading the answer, and finally predicting the accuracy. So let's run this. Here we are loading the dataset now. So we got sample 1 and sample 2. So here are our ground truth and LLM responses. For some responses, LLM predicted accurately. For some, it predicted wrong, and the overall accuracy is 0.9. Now let's see how to use LM Eval with the same dataset. In the above code cell, we had written multiple code lines to import dataset, import the task, predict accuracy. But with LM Eval, we can just do in few lines of code. So here we are passing the model. This time we are passing a different model, which is pre-trained GPT-2, and we are just loading the task BLEU, and we are defining zero shot or few shot, If we want to pass 0 shot, then we will pass 0 here. If it's few shot, we will pass the number of few shot examples you want to pass to the model. And within just few lines of code, we can get the results. And here we are plotting the accuracies. Let's run it and see how it runs. Let's load the model here. Now the model is predicting responses. So here we got the performance with pre-trained GPT-2 for BLEU. We scored around 40%. So let's run a different dataset this time, MMLU. MMLU is Massive Multitask Language Understanding. It's a comprehensive benchmark designed to measure models' world knowledge and reasoning ability. It has different domains like STEM, humanities, social sciences, and business, law, high school, and college level exams. And this format is basically multiple choice questions with different options. Why does this dataset matter? Because it tests broad factual knowledge and cross-domain reasoning. Here is one of the examples from the MMLU dataset. For example, you have a question like, which of the following best describes the function of ribosomes? You have multiple options and the model has correct answer, and we will compare this answer, ground truth answer, with model predicted answer. So let's run again MMLU dataset with OpenAI model. Here we are loading the dataset, reading the question, choices, answer, and we are passing the prompt. Your helpful AI assistant, choose the correct option for the following multiple choice question. And we are calling the GPT-3.5 Turbo model for response. Here is the overall MMLU accuracy for high school physics. We scored 40%. Here are some of the sample questions and responses from the model. So now let's use LLM and see that within few lines of code, we can generate the responses for the same task. Now the model is generating responses. So here is the performance on pre-trained GPT-2 model on MMLU high school physics. We got around 30% accuracy. Let's get into another task, GSM-8K. GSM-8K is a high-quality math dataset. Why GSM-8K is challenging? Because problem requires 2 to 8 reasoning steps. Answer cannot be guessed from surface patterns. Small arithmetic errors can lead to complete failure. Here is some sample question. Olivia has $23. She bought 5 bagels for $3 each. How much money does she have left? This is the solution or the ground truth. The cost of bagels is 5 into 3, which is 15, and remaining money is 23 minus 15 and $8. This is our expected answer. Let's run GSM-8K on the GPT-4 models and see what is our performance. We loaded the dataset and now we are generating responses from GPT-4. Here we see the performance of GPT-4 on GSM 8K dataset. We scored around 80% on this dataset. Let's check a different dataset, multilingual task, SQUAD Spanish. SQUAD is a cross-lingual question answering dataset, is a benchmark for evaluating multilingual reading comprehension. Basically, it has a Spanish context and question and the reference answer. Let's see on this multilingual dataset how our GPT-4 model performs. We will use the same LLM harness for evaluating this, which can be done in 4 lines of code. We can see that on multilingual SQUAD dataset Spanish, we scored around 53%. We can even use LLM on Indic languages like Hindi. MLQA Hindi is an Indic language dataset. Basically, it consists of multilingual question answering. It's a benchmark for evaluating cross-lingual extractive question answering. It contains around 12K question answer pairs on different languages. And it has 7 Indian languages including Hindi. Here is an example from MLQA in Hindi. We have a context about Mahatma Gandhiji and question about when Mahatma Gandhiji was born, and we have a reference answer. Let's see how our GPT model performs on this dataset. Now we are downloading the data. On MLQA Hindi, GPT-3.5 model performed with 40% accuracy. And that's it. You have now seen how to operationalize LLM evaluation using both standard benchmarks and flexible rubric-based scoring. Whether you are benchmarking a new model, tracking regressions in a deployment pipeline, or tuning prompts for a niche domain, these techniques let you test what matters most. Coming up next, we'll step back and look at real-world applications of all this. How companies use these evaluations in healthcare, finance, and education. What goes into safety and robustness testing, and how evaluation affects business value and user trust. Let's continue. Let's bring everything down to earth now, because everything we have talked about so far, from LLMs judging each other to generating synthetic benchmarks at scale, this isn't just theoretical. It's not some futuristic vision. These ideas are already in action today, in real companies, solving real problems, in some of the most high-stake domains you can imagine. And here's the truth that every LLM team eventually learns. Evaluations isn't optional. It's how you protect your users, your product, and your brand. Let's walk through where this is actually happening and why it matters so much. Let's start with healthcare. Imagine a clinical assistant powered by an LLM, helping a nurse triage symptoms or summarizing a patient's past medical records for a doctor. Or maybe it's a chatbot that answers common questions about medications or follow-up instructions. Now, think about this. It's not enough for the answer to sound fluent or polite. It needs to be factually correct. It needs to maintain a calm, reassuring tone, and most importantly, it must not invent information. That's why healthcare teams are now using LLM-based rubric scoring, asking models like GPT-4 to score responses on safety, clarity, and factuality. They even build custom evaluation datasets from real-world clinical notes. Some even run bias tests to check whether the model treats patient queries differently based on demographics. The stakes are high, and so the evaluation has to be airtight. Now, Let's switch gears to finance, another domain where hallucinations can be costly. Picture a customer asking an AI assistant, "What are the capital gains tax rules in my state?" or "How do I increase my credit score?" If the LLM gives even a slightly incorrect information, that's not just a poor user experience, it's a compliance risk. That's why financial teams are building custom evaluators that fact check against regulatory data, use rubrics for correctness and helpfulness, and test with adversarial prompts like, "How can I legally avoid paying taxes?" They are not just testing for truth, they are testing for intent manipulation. That's where evaluation frameworks earn their keep. Over in education, the landscape is shifting too. LLMs are now helping students learn as tutors or even as automated graders. But this space introduces a different challenge: subjectivity. Say, a student writes an essay or answers a math problem in an unusual but valid way. Will the LLM reward creativity or penalize it? That's why educators use evaluation setups where GPT-4 not only grades the answer but also justifies its reasoning. The model gets scored not just on accuracy but on clarity, tone, and alignment with learning objectives. Because education isn't about one right answer, it's about communicating, understanding. Now, let's talk safety, specifically red teaming. This is where researchers or security teams deliberately try to break the model by feeding it risky edge case prompts to see how it behaves. Can it be tricked into revealing harmful advice? Will it respond to toxic language? Will it stay aligned with safety principles? And get this, LLMs can actually be used to generate these red team prompts. Then, a rubric, often another LLM, scores the model's response. Did it reject the request? Did it flag the content? Did it redirect safety? This is a continuous process. Many companies run automated red team suits regularly to keep models in check after updates. Then, there is a challenge of long context models like GPT-4 Turbo, Claude, or Gemini, which can process entire documents or even meeting transcripts. But just because a model can read 10K tokens doesn't mean it actually uses them well. That's where evaluations like needle in a haystack test come in. Here's how it works. You bury a specific fact deep inside a huge block of text. Then ask the model a question that requires that fact. If it finds, it's great. If not, well, then you have got some tuning to do. Teams use synthetic data to simulate these scenarios, then evaluate retrieval accuracy and reasoning depth with LLM-based judges. Finally, let's talk about enterprise. Companies that fine-tune their own LLMs, maybe for legal contract summarizations, insurance code generation, or even internal support, often build custom dashboards for continuous evaluation. These dashboards track model performance across different versions, highlight safety regressions, and score outputs against business KPIs, like reducing ticket escalations or increasing resolution speed. Behind the scenes, they are running a mix of LLM as a judge setups, regression tests, and task-specific rubrics. For them, evaluation is part of the production pipeline, not an afterthought. Coming up next, we will look at the hard stuff that still isn't solved. We'll talk about bias in LLM judges, benchmark leakage, distribution drift, and why even with all these tools, we still don't have an universal standard for evaluating these models. Let's tackle the open challenges. Alright, let's pause for a moment and look around. We have covered a lot, from old school metrics to synthetic benchmarks, to letting LLMs judge other LLMs, and we have seen some seriously impressive tooling emerge. But here's the thing, this is still a young and rapidly evolving field. And if we look just below the surface, there are some big challenges we are still grappling with. Some are deeply technical, others are more philosophical questions about fairness, bias, and even what good behavior really means. But all of them matter, because if we get the evaluation wrong, we risk trusting models that simply shouldn't be trusted. So, let's break down what's still broken and where we need to do better. Let's start with a subtle but critical one, evaluator bias. When you're using one LLM to judge another, you're relying on its internal preferences, whether you realize it or not. For example, Some models just tend to prefer longer answers. Others might reward responses that sound formal, even if they're actually wrong. Some judges might be more lenient on some factual slips. Others might penalize heavily. That's what we call evaluator bias. And here's the scary part. Even if your evaluation model is solid, a biased judge can make the results look skewed or worse, misleading. Now, there are ways to reduce this. You can use multiple judge models and take consensus. You can shuffle the order of responses to avoid positional bias, or even build meta-evaluator systems that check whether your judge is evaluating fairly. But the risk doesn't go away. It just becomes something we need to monitor constantly. Next up, something a little sneakier, benchmark leakage. This one's like the dirty secret of LLM evaluation. You might think your benchmark is fresh, carefully curated, a clean test set. But what if your model has already seen it? Maybe during pre-training, maybe from public GitHub repo, maybe as part of a scraped dataset. If that happens, it's no longer a test, it's a memory recall. And when your model aces it, you get false confidence. You think it's generalizing when it's actually just repeating. This happens more than we would like to admit because many benchmarks are public, pre-training datasets are enormous and often uncurated, and even niche tasks can slip in through the cracks. How do we fight this? One way is to use dynamically generated benchmarks made on the fly. Another is to randomize samples every run, and if possible, cross-check training data to rule out known overlaps. But again, it's tricky. Leakage isn't always obvious, and the cost is misleading results. Now, let's talk about drift. More specifically, distribution drift. Here's what that means. Benchmarks are basically snapshots. They capture the world at a point in time. But the world moves on. Laws change. APIs update. Language evolves. Social expectations shift. So, if you're evaluating a model in 2025 using a benchmark built in 2021, well, you're not testing real-world readiness. You are testing history, and in a fast-moving domain like AI, that's a problem. To stay current, we need benchmarks that evolve. That means regularly updating test cases, feeding in new failure examples, and leaning more into live evaluation loops where users or humans in the loop keep the test bed fresh. It's not just about keeping up, it's about staying relevant. And finally, perhaps the most complex issue of all, the lack of standardization, especially around reasoning and alignment. Let's be honest, we still don't have a shared definition of what reasoning really is or what counts as aligned behavior. One team's idea of a helpful answer might be another's definition of a biased. Some groups value creativity, others want strict factuality. Some want models that defer to humans, others want to suggest boldly. Without shared rubrics or norms, it's hard to compare models fairly across organizations or even research papers. Now there is progress. Communities like Anthropic are pioneering value-aligned rubrics with constitutional AI. Stanford's HELM project and the GAIA leaderboard are working towards more open, multidimensional benchmarks. But there's still a long road ahead. And until we build transparent, collaborative, and auditable standards, these evaluations will remain a bit fuzzy. Each of these problems touches every part of the stack, from traditional metrics to the most modern LLM as a judge pipelines and solving them. That's how we build fair, reliable, and future-proof evaluation systems. Now, in our final chapter, we are going to look ahead. What's next for LLM evaluation? From multi-model committees to hybrid human-AI feedback loops to synthetic benchmarks that evolve in real time. We will explore where the field is heading and what it's going to take to build evaluation systems we can truly trust. We have covered a lot, from outdated metrics like BLEU and ROUGE to LLMs judging other LLMs, to benchmarks that adapt and evolve in real time. But here's the truth, evaluation is still a moving target, and the future, it's full of potential. So, what's next? A multi-judge system, just like real-world review panels. Future evaluators will combine insights from multiple LLMs. Think of it as peer review, but automated, live, continually updating benchmarks. No more static test sets. Imagine a real-time stream of fresh, domain-relevant evals, always current, always challenging. Hybrid human LLM loops. Machines bring speed and scale. Humans bring context and judgment. Together, they build evaluations that are both scalable and trustworthy. Because at the end of the day, evaluation isn't just about scoring models, it's about building trust. Trust that they are accurate, trust that they are safe, trust that they will work in the real world. So, whether you are launching a product, training a model, or just exploring, make evaluation part of your DNA because great models deserve great measurement. And now, you have got the playbook to make it happen. Let's keep building. See you at the next one.